When an electrical potential or voltage is induced in a conductor that's part of a complete circuit, current flows through the circuit. In many applications, the current flows first in one direction and then in the opposite direction. Current that changes directions in this way is called alternating current. Let's look at an example to see how alternating current can be produced. This demonstration includes a conductor in a stationary magnetic field. The conductor isn't moving, so there's no voltage and no current. To make what happens easier to follow, we'll represent the changes in direction on a graph. One axis on the graph represents the induced voltage, and the other axis represents time. As the conductor rotates through the magnetic field in a clockwise direction, the induced voltage first builds up from zero to a peak or maximum value in one direction. We'll call that direction positive. As the conductor continues to rotate, the voltage returns to zero. It then changes direction, builds up to a peak or maximum value in the negative direction, and returns to zero again. At this point, the voltage has completed a full cycle. This curve is called a sine wave. Now, in an actual power system, cycles occur rapidly. In many cases, there are 60 complete cycles each second. The unit that represents cycles per second is Hertz, so 60 cycles per second can be referred to as 60 Hertz. The value of the induced voltage is at a peak 2 times during each cycle. Since the value of the voltage is continually changing, the peak voltage value is not the true or effective value of the voltage that's produced during the cycle. Instead, the effective voltage is an average value. In most cases, the average that's used is called the root mean square, or RMS value. The term root mean square refers to the mathematical method that's used to calculate the average of the different voltage values in a cycle. For simplicity, the RMS value is usually given as 0.707 times the peak value. That's accurate enough for most situations. Well, we've seen how AC voltage is produced and how it changes, and we've seen how these changes can be represented by a sine wave. The sine waves we've looked at so far are single-phase sine waves. They represent power produced by single-phase generators. However, most large industrial equipment operates using three-phase AC power. Let's take a look at what this means. In this illustration, the conductor consists of 3 equally spaced coils or loops. As these loops rotate through the magnetic field, each loop produces voltage that can be represented by a sine wave. This illustration shows the voltage sine waves for the 3 loops. You'll notice that even though at individual times each sine wave becomes zero, the sine waves are never zero for 2 phases at the same time. This means that the effective voltage and current produced by this 3-phase arrangement are never zero while it's operating. In this topic, we learned about electricity. We discussed electrical potential and some sources of electrical potential. We also covered magnetism and alternating current. Now try a few practice questions to check what you've learned. The forces related to the movement of electrons can be referred to as electromotive forces, or EMF. EMF is one way of expressing electrical potential. Another term that is used interchangeably with electrical potential is voltage. A third source of electrical potential is light. Light may be a great source of electricity in the future. The principle of producing electricity by using light is referred to as the photoelectric effect. To make what happens easier to follow, we'll represent the changes in direction on a graph. One axis on the graph represents the induced voltage, and the other axis represents time. As the conductor rotates through the magnetic field in a clockwise direction, the induced voltage first builds up from zero to a peak or maximum value in one direction. We'll call that direction positive. As the conductor continues to rotate, the voltage returns to zero. It then changes direction, builds up to a peak or maximum value in the negative direction, and returns to zero again. At this point, the voltage has completed a full cycle. Basically, a motor is a device that uses electrical energy to produce mechanical energy. Let's use a demonstration to understand this better. This is a very simple example of an electric motor. It consists of 2 bar magnets and a rotor. The rotor is the part of the motor that moves or rotates. The 2 bar magnets which do not move are called the stator. copper conducting wire is wound around the arms of the rotor. The rotor is connected to a shaft. In order to operate, the motor must be part of an electrical circuit. In this circuit, a battery is the source of electricity, and a switch is used as a control device. When the switch is closed, a complete path is formed, and current flows through the conducting wire. As you can see, the rotor is spinning, causing the shaft to rotate. The motion results from the interaction between two magnetic fields. One of the magnetic fields is produced by the bar magnets. We'll call this field the stator's magnetic field. The other magnetic field is the rotor's magnetic field. It is a result of the current passing through the conducting wire. Whenever current passes through a conductor, a magnetic field is created around the conductor. This type of magnetic field is called an electromagnetic field. If the shaft in this motor were connected to a mechanical device, it could be used to drive the device. Motors come in many different sizes and designs. The variations allow motors to be used in many different applications. Regardless of the particular design of a motor, however, the principle of operation is the same for all motors. That is, the rotor's magnetic field interacts with the stator's magnetic field, causing the rotor to rotate. Direct current, or DC, is current that flows in one direction. In a DC motor, direct current flows through a conductor and creates a magnetic field around the conductor. This magnetic field interacts with another magnetic field to produce motion. Let's look at a demonstration to see how a DC motor operates. The stator, or stationary part of this model, is a horseshoe magnet. The rotor, or rotating part, is simply a coil of conducting wire wound around a metal core. A battery supplies electricity to the motor. When current flows through the rotor's coil, it causes the rotor to become an electromagnet. The attraction and repulsion between the poles of the horseshoe magnet and the poles of the rotor cause the rotor to turn. During operation, the rotor must continuously switch polarity in order to maintain motion. In other words, the north and south poles of the rotor must switch. The parts of the motor that cause the poles to switch are a commutator and brushes. The commutator in this arrangement is a small copper conducting cylinder that is split into two halves. These two contact strips that touch the commutator are the brushes. When the motor is operating, current flows from the negative side of the battery through one of the brushes, then through one half of the commutator and onto the rotor. After the current flows through the rotor, it flows to the other half of the commutator, then through the other brush. And finally, it returns to the positive side of the battery. The commutator and the brushes constantly change the direction of current flow to the rotor. That's what changes the polarity of the rotor. Now let's take a look at how the commutator, brushes, and rotor windings cause a DC motor to work. This horseshoe magnet is the motor's stator. The north and south poles are indicated by the letters N and S. The poles of the rotor are indicated in a similar way. When the rotor is in this position, the north pole of the rotor is repelled by the north pole of the stator and attracted by the south pole of the stator. Similarly, the south pole of the rotor is repelled by the south pole of the stator and attracted by the north pole. The combined effect of these attractions and repulsions moves the rotor. At this point, the commutator and brushes switch the direction of current flow through the rotor coil. The change in current flow direction switches the polarity of the rotor. This change in polarity keeps the rotor rotating in the same direction. It continually moves toward opposite poles. This continuous process of switching polarity causes the magnetic fields in a DC motor to change positions. That's what causes a DC motor to operate.